So we've talked at some length about strain, and then we've talked about stress. Now it's time to put these two ideas together in the form of a constitutive equation that relate stress and strain. So we're going to start talking about what are called the equations of elasticity. We're talking about elastic material response, and basically that's a subset of a general field of constitutive modeling, and constitutive modeling relates stresses and strains to each other. Well, we can get a little bit of insight into constitutive modeling, and in particular elastic material behavior, by examining the uniaxial response of a material. In general, we could have multiaxial response. We can have a full stress tensor and a full strain tensor related to one another. But for the simple case of uniaxial tension, we can take a look at some of the typical responses of metals in particular. So let me clear off this page and we'll draw a sketch of the basic response of stress and strain in a metal. Let's talk just a little bit about how a tension test is typically conducted. We take a bar that has a certain gauge section that I've drawn here on the right side of my picture, and attached to this is an extensometer. It's a little electrical device with some wires that go off, and it measures the extension of an initial gauge length. So the L0 may be an initial gauge length, and it gives an electrical signal that's proportional to the change in that gauge length. These tests are often conducted in what's called displacement control, so that this section may move up while the bottom section stays fixed, and it moves up at a certain displacement rate, maybe 1 inch per minute or 20 millimeters per minute, or whatever displacement rate is specified in your particular kind of material you want to do a tension test on. At that same time as the displacement is increasing, it takes usually an ever-increasing amount of force, up to a certain point, to stretch out that bar even further. Okay, so what I mean by that is if we were to look at the force versus displacement curve that I'll draw over here, if there's no displacement, there's no force. There's a little bit of displacement, there's more force, and initially it's kind of proportional to one another. So double the displacement means double the force. And so this curve kind of comes along as kind of a straight line for a lot of materials. We'll talk about some things that happen when we start to have yielding, but maybe it does something like this, and maybe it's a peak and it comes down and it breaks. Now remember, we are testing in displacement control, so basically we're specifying some amount of delta L that this bar can have along this axis. And this is our independent variable, and our dependent variable then would be the force. So this would come up, the force may increase, the force may decrease a little bit here, may hit a peak force, and it may come down and break. So after a certain point, we have less amount of force required to get even more stretching in the material. This is a special point related to necking in the material, and we'll describe what that means in a moment. Well, we know that there are different definitions for stress and strain. We've talked about engineering stress and engineering strain. We've talked about different forms of strain, such as the Green-St. Venant strain, the Almansi strain tensor, and so forth, Cauchy strains. We can have similar definitions for stress. We can have stress is equal to the force divided by the original cross-sectional area, or stress is equal to the force divided by the instantaneous cross-sectional area. For now, let's take a look at stress divided by the original cross-sectional area. Stress is equal to force divided by the original cross-sectional area, and we're going to define our strain as an engineering strain, the change in length divided by the original length. Since we're taking this force and dividing it by a constant, we effectively get a different scaling on our force response, and likewise with the strain response. So these look like very similar shapes. So let me come back over here and just sketch that on this plot. So maybe it comes up kind of nice and straight. It might do a little bit of stuff over here. It might come down, might come back up, and hit a peak and come down. We won't spend a lot of time talking about different parts of the stress strain curve, but for a low carbon steel, this is pretty typical. A 1008 steel, something like that. This would be your upper yield stress. This would be your lower yield stress. And the yield stresses are positions where we have permanent deformation. This would be our ultimate stress. And the reason why the load drops once we hit a certain point is kind of artificial in the fact that we're dividing by the original cross-sectional area. What happens at this point is at this point in the material we have what's called necking. There's kind of a dent that forms in the material. And because of that reduced cross-sectional area locally, we have a non-uniform strain distribution for one thing, but we have a much reduced capacity to carry additional load. So the load goes down even though the stretching out gets more. The initial portion of the stress strain curve for most metals is pretty straight. And this is a cartoon that I've sketched here. The slope right here is not this shallow. The slope is actually very steep. If you were to plot this to scale, the initial portion of the stress strain curve would be almost on the vertical axis before all this other stuff happens. The slope of the stress strain curve in the elastic region is called the modulus of elasticity E. So this would be the change in strain over a certain change in stress. Some people call it Young's modulus. Some people call it the modulus of elasticity. And it's only valid to determine the modulus of elasticity from this method when stresses are less than the yield stress of the material. And we can be even more precise. We can say when they're less than the elastic limit of the material or the proportional limit of the material. In other words, when it stops being a straight line, we can't use the slope of a straight line to determine our modulus of elasticity anymore. And that makes a lot of sense. If we were to plot true stress versus true strain, initially the curve would look very similar. Might start to see a little bit of difference. We wouldn't see much difference until we got above the ultimate stress. The true stress is the force divided by the instantaneous area, and the true strain we would write as the integral from the initial gauge length to the current gauge length of dl over L. And it never really falls. Once it gets past the ultimate, it starts to separate a little bit before the ultimate, but it doesn't fall. It keeps to increase because the stress really does go up when this area gets real small. It's just that it's not accounted for in the engineering stress definition. So if I were teaching a class in plasticity, we would talk a lot more about what happens after the yield stress of the material. But since this is a course in elasticity, we're going to focus on the initial portion of the stress strain curve where stresses and strains are typically linearly related to one another. It is possible to have nonlinear elasticity, and we'll give a more formal definition of what elasticity means here pretty soon. But from the point of view of a tensile test of a material, particularly low carbon steel, this is kind of what we would get. There are other common materials that don't have this double yield point behavior, upper and lower yield stress. Materials like titanium and aluminum typically don't have an upper and lower, and I'll draw a sketch of that next. And so here's an example. Again, this is more of a pictogram than what an actual stress strain curve would look like. This would be very steep, but we can still define a modulus of elasticity as the slope of the initial portion of the stress strain curve, and it kind of more smoothly transitions from the straight line to hit a peak, coming on down for the engineering stress strain curve. So there are different ways that we can define our elasticity. One way to define elasticity is it's the stress level that you can go to where if you load it to that level and then unload it, you return back to zero stress and strain. So what happens with materials, you can think of this like a spring, is that when you load them, you can have permanent deformation. If you have a spiral notebook and you have one of these springs, you can stretch out that spring and you can make it longer. And that spring then, if you unload it, will go back to its original size. And that would be elastic behavior. But there are some instances where you can take the same spring and you can really stretch it out, and when you unload it, you may have some permanent deformation. And this is known as inelastic or plastic deformation. Well, the same thing is true with materials like our aluminum that I have shown here. If we load it up and get a certain amount of stress and we unload it, we will unload back to right about here. If we go too high, like maybe up here, we have exceeded the yield stress of the material. The unloading path would follow this curve, and we would have some permanent deformation. Or some plastic deformation. So in our class, we're going to focus on what happens when materials do return back to their original dimensions. Now, it's not very practical in a tension test to load and unload something. When you put it in a tension test, you continue to stretch it out, and the forces keep increasing until they hit the necking point of the material, where then it starts to decrease. We don't ever unload it and measure the dimensions and say, okay, it's okay here, but it's just 1 over, I don't know, 0.001 millimeters longer. Now we have permanent deformation. We don't do that way. But we do something called a 0.2% offset yield stress, and we can get into those details. I do teach a class in mechanics materials and talk about laboratory results for mechanics materials lab. And I do have other classes and videos where I go into that level of detail as to when we have permanent deformation and so forth. So let's write this down. Elastic material behavior can be defined, one way to define it, as the complete recovery of deformation upon unloading. And although we're going to talk about elastic material behavior, there are different types of material behavior that can be accounted for, and each have their own unique name. So we have elasticity, which is an instantaneous recovery or complete recovery. We can talk about something called viscoelasticity. Some rubber materials exhibit viscoelastic material behavior. This could be thought of as a time-dependent recovery. We can talk about plasticity, which is kind of rate-independent, permanent deformation of material. Most metals are actually elastic plastic in behavior beyond the yield stress. Of course, plasticity is an important field in the study of metal forming, stamping operations, machine cutting of materials, and so forth. And we can look at viscoplasticity. So it's time-dependent, permanent deformation. And we can make a huge list of different areas of constitutive modeling, but these are pretty common. We have ways that we can incorporate thermal effects into this. We can incorporate electromechanical and magnetomechanical effects. All kinds of interesting sensor type technology that material may strain and then exhibit an electrical response. Piezoelectrics, for example. But again, for us, we're going to focus on elasticity in this class, as that's what this one's all about. With a good foundation in understanding elasticity and stresses and strain, it makes studying all these other different areas a lot easier. All right. So we have just talked about how elasticity is the material returning to its initial state or its initial dimensions upon unloading. There is a functional relationship between stress and strain because loads are related to changes in dimension of a structure. Stresses are related to loads and strains are related to changes in dimension, and then so therefore stress and strain are related to one another. Now there is an alternative way besides thinking about dimensions and recovery of dimension that we can define elasticity by. And we can say that elastic material behavior can be defined as a complete energy recovery through one full load-unload cycle. Well, let's think about what that means a little bit. If we have a material like our tensile specimen, either steel or aluminum, whichever one we want to think about, and here's our stress-strain curve. If we're below the proportional limit stress, and this is a straight line relationship, we're below the yield stress of the material, so we have elastic loading, elastic material behavior. If we load it up here and we unload it, we go back to the origin of our stress-strain curve. If we don't have any permanent deformation, that's the change in dimension concept. But as we load it, we can think of us as storing energy in the material. And that energy in the material expressed as an energy density is the area underneath the stress-strain curve. For a linear elastic material, this is very nice. It forms a triangle. So this would be 1/2 sigma epsilon. It has units of energy divided by volume, so that's why we call it energy density. Of course, the stress is the force divided by area, and strain is the change in length divided by a length. The area times the length gives us a volume, and the force times the change in length is an energy or a work type of term. So the alternative definition of elasticity then is that when we load it up, we're putting energy into the material, and when we're unloading it, we're recovering that energy out of the material. Now we do have to stop here and think about this a little bit. Does any mechanical process really completely 100% involve absolutely no energy losses? Well, no, but things like mechanical springs are very efficient at energy transfer, and you don't lose very much. I am not saying that a material will be exactly the same every time you load it. There are atoms in materials, like metals. There are things called slip systems. And these things, and dislocations in metals in particular, will move atoms around, and things don't exactly go back to where they were before you loaded it. And that's the whole process of fatigue damage in materials. You can have fatigue damage while you're still below the yield stress of the material due to these slip systems and dislocations moving around inside crystals and grains and free surfaces of metals. But for an idea and an assumption, it's a very good assumption to assume that we have complete and full energy recovery through one load and unload cycle. Now at this point we're going to get a little bit more into the mathematics that describe what happens and how we can model what goes on in elastic material behavior. We're going to start with something called an intrinsic strain energy density function, F. Alright, let's break that down a little bit. Intrinsic means something associated with the material. A different material may have a different intrinsic strain energy density function. We've talked about energy density. Okay, it's a work per volume. Okay. And what I've written down on the next line is that delta I, variation in internal energy, the work required to deform a volume of dV, is equal to this intrinsic strain energy density function times the volume that it's acting on. Okay, so let's label this. So the work that's required is going to be equal to the energy that can be stored in this intrinsic strain energy density function times the volume that it's acting on, because remember, it's an energy density. Now there are some things that we're going to assume as we go through this process. We're going to assume that we have an adiabatic process. Probably talk about those if you have a class in thermodynamics. For us, what that means is that there's no heat loss. We're going to use what are called conservative forces. And its final state of this material is not dependent on the load path or the deformation path. Okay, so the last one, what I mean by that is if you take a material and pull on it and then twist it, we'll end up with the same material state as if we were to twist it first and then pull on it. That is not the case if we have inelastic or plastic deformation. Pulling and twisting may give you a different final strain state or stress state than if you do the opposite. Now there are different ways that we can write the epsilon dependence on F. We can write it in terms of strain tensor components. Epsilon 1,1, epsilon 2,2, epsilon 3,3, the normal strains, and we can write it with the shearing strains. I'm writing here with tensor shearing strains, epsilon 1,2, epsilon 1,3, and epsilon 2,3. Here we have a symmetric strain tensor, or we can write it in terms of principal strains if we want. Epsilon 1, epsilon 2, epsilon 3, and the angles that it takes to get to those particular directions. We call these angles maybe theta, phi, and psi. So either way, and it kind of depends on what we're looking at as to which form we might want to use. Let me make a little bit more room. We'll talk about isotropy and anisotropy. So if the intrinsic strain energy density function depends on direction, then that material would be considered to be anisotropic, behaves differently in different directions. Otherwise, if it does not depend on direction, it is isotropic. So the second form that I've written here, the F of epsilon principal strain 1, 2, and 3, theta, phi, and psi, that depends on direction. But if it doesn't depend on which direction, we have symmetry among the principal strain directions. Then we would have a reduction here that we can write the intrinsic strain energy density function just in terms of the three principal strains, epsilon 1, 2, and 3. In terms of writing it in terms of the three principal strains, epsilon 1, 2, and 3, we could write this in terms of strain invariance, and I'm going to use a different F, use a script F. If we call our strain invariance J1, J2, and J3, we can have a slightly different looking function in terms of these quantities as well. Well, with this intrinsic strain energy density function that represents what goes on in a small volume of material, if we integrate that over the entire volume of the body, then we can get the work expended by the entire body. So I would be equal to an integral over the volume of this F as a function of J1, J2, and J3 for an isotropic material. Now the next thing we want to do is we want to get stress into all of this. And so we're going to look at stress and the strain energy density function. And we are going to be restricting ourselves to the small strain assumption that we have. So our strain displacement relations will neglect the higher order terms. So let's take a look again at a small amount of work required to deform dV. That's this variation in I. So it's the variation in what goes on for this body integrated over the volume for the strain energy density function dV. And if we have a conservative system with no energy losses, it's adiabatic, that will be equal to the change or the variation in the work done by external forces. So let's write a little bit of this down. Small amount of work required to deform that little bit of volume is equal to the variation in energy in a volume equal to the change or variation in work done by external forces. And to make it clear, we have no particular losses. Now the way we can get stress in here is by looking at the right-hand side, looking at the work done. And for bodies in equilibrium, we typically have two types of forces. We have surface forces or tractions and body forces. So this variation in work will be the variation in work done by the body forces plus the variation in work done by surface tractions. Let's take a look at the body force term first. So variation, the work, body forces, we can express that as a volume integral of the body force components V sub j times some variational displacement, variation of U sub j dV. So U is a displacement vector component, and the delta Uj term is a variation of displacement. Now, what do we mean by a variation in displacement? So, if we have a certain direction that this thing may want to move, we can assume that it moves just a very tiny amount in that direction, kind of an infinitesimal amount, a virtual displacement, a small variation in that displacement component in order to get a small variation in the work. For the other term, the work of the surface forces, we have a little bit more we can do with that. We know that we can express this in terms of tractions, again times a small variation in displacement. So T sub j, the traction vector components, times delta Uj with an applied summation integrated over the surface. We know that whenever we have some sort of, we know we can replace this traction vector with the stress, because in general T sub L is equal to sigma Lm in m. It's our traction vector and stress relationship. So in this particular case, what I'm going to do is I'm going to replace this T sub j with a sigma ij in I, variation in Uj. And by the use of the divergence theorem, then we can replace this as a volume integral. The partial with respect to xi, this quantity sigma ij, variation uj dv. Stress tensor being symmetric, I can write it with the n sub I. Alright, so I'm going to put these together. Let me make a little bit of room. We can express this in terms of a volume integral of these two terms. The first term we're going to write is with one with attractions. We're going to partial with respect to x sub I of sigma ij delta uj. And then the next one with the body force terms, the b sub j delta uj. This partial derivative, we can expand that out by our product rule. So the first term times the second. In this variation and partial differentiation, we can kind of move those around as we would like. They're first order. So we have the variation of the partial derivative uj with respect to xi. Second term we have the partial derivative of sigma ij with respect to xi, variation uj plus bj variation uj. And now we're going to take a look at this first term in a little bit more detail. So what we have is sigma ij, variation partial of u sub j with respect to x sub I. Now let's go ahead and write all 9 terms in this expansion out, and let's see what we get. I won't say all of them, but we'll go through with I and j is equal to 1 and 1, and then 1 and 2, and so forth. It'll take me just a moment to write all these down. And I will really try hard not to make any mistake in any of these subscripts, but sometimes those things happen. So do keep a close eye on what I'm writing down. Now we'll start with the last row of added terms. Sigma 3,1, variation of partial derivative of u, that would be u1 with respect to x3. 3,2. There we go. That's better. And then the last one is 3,3. And so we have all those 9 terms. Let me make a little bit of room. Now, for small deformation strains, we know that we have the relationship epsilon ij. Let's see if I can get that fixed there. Small strain relations that epsilon ij is equal to 1/2 partial derivative of u sub I with respect to x sub j plus the partial derivative of u sub j with respect to x sub I. So if we look at our first term, sigma 1, 1, variation of the partial derivative of u1 with respect to x1, then we can directly rewrite this as sigma 1, 1, variation epsilon 1, 1. And we have two other terms that we can do that to. So if I and j are both 1, we have 1/2 of this term, which appears twice, which is this term, partial of u1 with respect to x1. We also have terms that are like sigma 1, 2, variation of u2 with respect to x1, plus sigma 2, 1, variation of partial of u1 with respect to x2. Since the stress tensor is symmetric, we can pull these together out in front, and we can write it like this. Usually I put the partial of u1 with respect to x2 first. Let's do it this way though. We can pull like the variation out, and we would have partial derivative of u1 with respect to x2 plus the partial derivative of u2 with respect to x1. And what that term in brackets is 2 times the variation in the tensor strain component epsilon 1, 2. Now, if we wanted to, we could rewrite this slightly differently as well. We could say it's sigma 1, 2 times the variation in epsilon 1, 2 plus sigma 2, 1 times the variation in epsilon 2, 1. Alright, now with that, we can go back to our equation on top. In variation and work, we can express then as an integral over the volume of sigma ij, variation in epsilon ij, plus we have a term that looks like the partial derivative of sigma ij with respect to xi plus the body force term bj times variation in displacement uj, bracket and then dv. Now if the material is in equilibrium, this is 0. So this reduces down to the variation in the work is equal to an integral of the volume of sigma ij, variation in strain, epsilon ij, dv. Then that's equal to integral of the volume, variation of strain energy density function, dv. Let's look at this in just a little bit more detail. So now we have a fairly explicit definition that we can use for variation in intrinsic strain energy density function. There's going to be 9 terms in this expression. Let's go ahead and write them all out. We're going to get 3 terms that involve normal stresses and normal strains. We're going to get terms that are shear terms involving shear stresses and tensor shearing strains. Since it's symmetric, there's going to be a contribution from both pair. So we have 2 sigma 1, 2 variation in strain, tensor strain epsilon 1, 2. We get 2 of these other terms. And finally, the last pair of shear terms, 2 sigma 2, 3 variation epsilon 2, 3. Now we have some terms in here that look like stresses and we look like strains. There's a couple ways to write this, and we're going to follow what our book is doing. We're going to find this as a stress SI and a strain term E sub I. And we've talked about deviatoric stresses. These are not deviatoric stresses in this notation. They're defined completely by this equation that we have above. So our S 1, 2, 3, 4, 5, and 6 that vector, if we want, can be defined in terms of our stress components, the 3 normal stresses, and then the 3 shearing stresses. And our E, our strain type terms, those 6 components can be expressed in terms of the normal strain components, epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3. And then if we take that 2 and multiply it by the tensor shearing strain components, we get engineering shearing strain components. Which we can express with our symbol for gamma for the engineering shearing strain. So we have gamma 1, 2, gamma 1, 3, and gamma 2, 3. And let me use a different color. These would be our engineering shearing strain. So we have variation in intrinsic strain energy density function F is equal to our stress S sub I, variation in our strain terms E sub I with the implied summation there. Turns out this is an exact differential. Kind of hate that I'm fighting with my software package here. I keep thinking I've got everything disabled. But what this is an exact differential. We've talked about that at the beginning of the course. we have a path-independent conservative system. And what that implies is that we can have a potential function where our stresses are derivable from a potential function. I'll call that U star. So that S sub I then would be determined from the partial derivative of this potential function U star with respect to the strain components. Now, instead of using this particular funny notation with the S's and the E's, we can also go through this and write this in terms of stress tensor and strain tensor components. And this means that sigma ij can be determined from the partial derivative of this function u with respect to epsilon ij. Okay, so here u is a function that we need to find. Alright, well, this is a good place to stop for this particular lecture. And next time we're going to take a look at Hooke's law, which says that stress is a linear combination of strain and vice versa. And then we'll get into what I'm going to call material science notation and a tensor notation for Hooke's law. We'll dig into this potential function u in a little bit more detail.